Je kunt de camera muten, hè?
Dat werkt niet.
Jawel. Here's a mic for you. There you go.
Ja, jullie mogen zitten. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. Ik heet jullie van harte welkom bij de publieke verdediging van Silke Maes. En ik verklaar de zitting voor geopend. Silke Maes heeft aan de faculteit een proefschrift ingediend, handelend over modeling environments of evolved stars, morphology, chemical sensitivity en neural surrogate models. En dit tot het verkrijgen van de graad van de doctor in de wetenschappen fysica. Silke Maes zal dit proefschrift nu verdedigen. Ik vraag aan de kandidaten om een presentatie te geven van maximum 45 minuten. En daarna zal er de gelegenheid zijn tot het maken van opmerkingen en het stellen van vragen. Silke Maes heeft het woord.
Okay. Thank you very much. All right. So first of all, thank you all for joining me today. So that's correct. I will defend my PhD. And this presentation will be about modeling the environments of evolved stars. And I'll mainly do this with three different topics, namely morphology, chemical sensitivity, and neural surrogate models. You might have been wondering already, why are these weird lines here on the cover and why did I put them on my thesis? But I hope by the end of this presentation you will know why and you will understand these a bit better. So let us start from the beginning. So stars, they are born with quite a range of different masses. So we have the stars that are born with the lowest mass. Generally, they have a mass lower than the mass of the sun. So this circle symbol with a dot inside that stands for the sun. And we call these red dwarfs because they're quite tiny and because they are red in the sense that they are quite cool. Then we have stars that are similar to our sun. So also the mass of these stars is about the mass of the sun, and they shine generally in the yellow, just like our sun does. And then we have the massive stars. These are not only massive, they're also very bright and they're big. And they're also warmer than the low mass stars, hence they shine in the blue part of the electromagnetic spectrum. Now, these massive stars, they live a very short and violent life. Just in a nutshell, they evolve to explode as a supernova and they leave behind a black hole or a neutron star, depending on their initial mass. Although they're not the topic of today, so I won't go into further details. All the way on the other side of this mass range, we have the very low mass stars, and they live a very, very long life and also very quiet. There's even the majority of these stars don't even have had the time in this universe to evolve all the way to a white dwarf. But what we're interested in today are these sun-like stars and how they evolve and also a certain specific phase. So these sun-like stars, they live about 10 billion years like our sun, and about 90% of the time they live just in this first evolutionary phase. It's quite calm, and then after about 9 billion years or something, they evolve up to the asymptotic giant branch phase. Afterwards, they evolve to a planetary nebula to leave behind a white dwarf at the end of their life. And the evolutionary stage we're interested in today is this asymptotic giant branch phase. And I'll tell you more about this in a second. Now, it is a very nice image from ESA. It's not very much to scale. It rather looks something like this. It's not even up to scale, of course. But what I want to show you is that the phase where the sun is in now, it's quite tiny compared to the other evolutionary phases. So when the star evolves to the asymptotic giant branch phase, it really grows a lot, and it also becomes red because it becomes cooler. Then the planetary nebula phase is generally even bigger, and then all the way at the end, the white dwarf, this is an object that has about the size of the Earth, so it's quite tiny compared to the rest. Now let us have a closer look at these asymptotic giant branch stars. Now it's a quite annoying name, and I also already, yeah, it was hard to pronounce already a few times. So from now on, we'll just say AGB stars, which is much easier. I already mentioned these stars are quite large, so they have a radius of about 1 astronomical unit, and an astronomical unit is the size between the Earth and the Sun. So this means when also the Sun will evolve to this AGB phase, it will reach even Earth, and it might even engulf Earth inside its surface. I also already mentioned that these AGB stars are quite cool at their surface, about 2000 Kelvin. This might seem still like quite a lot compared to what we know from Earth, but if you compare this to the Sun is about 6000 Kelvin at its surface. So compared to this, AGB stars are quite cool, and therefore also they shine in the red part of the electromagnetic spectrum. Although they're cool, they're still very bright. And the brightness in astronomy we measure via the luminosity, and these AGB stars are about 1,000 times as bright or as luminous as the Sun. So this means that AGB stars are cool, bright, and huge stars. All the way in the center of these stars, we find a core that consists out of carbon and oxygen. Now, this carbon and oxygen, it was not always there. In the first evolutionary phase, so in the phase where the Sun is in now, there is still hydrogen and helium inside the core. So what happened? So there was nuclear fusion reactions going on, where first hydrogen was converted to helium, and then further this helium was converted to carbon and oxygen. And when these stars evolved up to the giant branch phase, they have a quiet core that exists out of this carbon and oxygen, and no further nuclear reactions are going on inside the core. However, around this core, there is still a shell that contains helium, and we say that it's still burning. So this means that there are still nuclear reactions going on. So in this shell, there is still helium converted to carbon and oxygen. Also, a bit further out, there's still another shell present that is still burning, namely containing hydrogen. And so in this shell, hydrogen is still converted to helium. Then the remainder of these HB stars, it's basically a very huge convective envelope. And I say huge because actually this inner part of the HB star, it's only a tiny fraction of the total volume. So it's about 1% of the size, although it contains about half of the mass. So this means that HB stars are really puffed up stars. So with a massive, or not, it's not massive, but compared to the rest of the stars, so it's quite a heavy core, but tiny, and then the rest of the envelope is very loosely bound. Now, I shortly already mentioned that this envelope is convective. This might not say much to you, but convection, that also happens when you try to boil water. Once water starts boiling, you have this turbulent boiling motion, and that's actually also what's going on in this envelope. And because of this boiling motion, there's a lot of movement, and it might be that the envelope penetrates these layers where there are still nuclear reactions going on, and this can cause S-process reactions. Now, what are these? These are also nuclear reactions that produce more heavy elements. So let us have a quick look at the periodic table. I think you've all seen it at some point in your life. So it's also a very important thing in astronomy. You might think this comes only from chemistry, but actually in astronomy, it's a very important thing. And why is this the case? This is because when the universe came to existence during the Big Bang, we only had hydrogen, helium, and lithium present. So this means that all the other elements that we find on Earth and that we just know in general are all produced inside stars or because of stars. And so today we're looking at these dying low mass stars, as it's indicated here. So these are the AGB stars I was talking about. So wherever you see like a green part inside the box of the element, these elements are partially produced by AGB stars. So as I already mentioned, there is the carbon and also a bit of oxygen that's important, but also as you can see, a lot of nitrogen is produced by the AGB stars. And then we also have these S-process elements that I mentioned shortly before. These are more heavier elements that are just produced or mainly produced by AGB stars, as you can see by the colors. So this means that AGB stars are very important in building this periodic table, and hence they are important in the enrichment of the interstellar medium. Now, the interstellar medium is basically all the material that we find in between stars. So there's not only material inside the stars, but also in between stars we find material. This can exist out of gas or dust. And as you can see here in these graphs, HB stars, they are a big contribution, especially to the gas. They contribute about 75% of all the gas we find in this interstellar medium, and also about 25% of the dust. So it's really important that we understand well the gas and the dust that HB stars bring to the interstellar medium. And why is this important to look at? What you can see here is an image of the Orion Nebula, and all the colored, yeah, cloud-like structures. This is the interstellar medium I was talking about, and these are also sites where new stars are born, and hence HB stars bring us the new building blocks of new generations of stars and planets. So in this way, also HB stars, they contribute to the life cycle of galaxies. Now, you might have been wondering, okay, it's all fine that these elements are produced inside the HB star, and now suddenly they are contributing to the galaxy. How do these elements, come out of the HB stars, basically? Well, there's another important aspect to HB stars, namely a stellar wind. And now, so what is a stellar wind? I'll go over this schematically. So in the case of HB stars, as I mentioned, we have this convective envelope. Because of the turbulent and boiling motion at the surface, this creates pulsations. And because of these pulsations, there are shocks created. So surface material of the star is really lifted up higher. And in these higher regions, temperatures are cooler, and hence dust grains can form. So there is dust sticking together, forming larger grains. Now, the HB stars, as I've told you, are quite cool, and therefore they shine in the infrared part of the electromagnetic spectrum. And now it happened to be, coincidence or not, that these dust grains can absorb very efficiently this infrared radiation, and so they take the momentum from the photon and use it themselves to accelerate outwards. Now, in this region where dust grains are present, there's also still gas present, and because the dust is now accelerated outwards, it drags along this gas. And in this way, we get a macroscopic outflow. And I hope, yes, you can see also on the projector the arrows that are going out. So really, we have a macroscopic outflow of material, and this creates a very big circumstellar envelope around the HB star. And it's actually this circumstellar envelope that is the topic of today. So I lied slightly in the beginning when I said it was going to be about HB stars. It's actually about their surroundings even. So from now on, we'll rather look at the system like this. So we have our HB star in the center, but further than that, we don't really care. But we care about this huge circumstellar envelope of material that came loose from the HB star and is now expanding in the interstellar medium. There are two main important parameters that we use to characterize such an outflow. And the first one is the mass loss rate. So this is the amount of mass that the HB star is constantly losing from its surface. We generally express it in solar masses per year, and it's only a very tiny fraction of the mass of the sun that is lost every year. Then the other stellar parameter, or the other parameter I mean for that's important for circumstellar envelopes is the expansion velocity, because this outflow is still expanding into free space, and generally it goes with a velocity of about 10 kilometers per second. That might seem like quite a high speed, kilometers per second, but actually in astronomy it's still quite slow. Okay, we're almost there for introducing these circumstellar envelopes. There's one crucial thing missing, which is astrochemistry. So these circumstellar envelopes, they have a very ideal combination of the right density and the right temperature where there is a lot of chemical reactions going on. So inside this outflow, I now only drew these molecules here, but they're actually everywhere. So in this circumstellar envelope, there is a lot of chemical reactions going on, molecules interacting with each other, breaking each other up and making new molecules. So also astrochemistry will be part of today's presentation. Now, up until now, I've also only drawn these circumstellar envelopes as nice circles, or in real life, there are, of course, spheres. And scientists have long been believing that indeed these objects are nicely spherically symmetric. However, recent observations show us that this is actually not the case. So what do we see here? We here see the observation of 10 different HB stars, and each time the HB star is just located in the very center. So we're actually looking at the circumstellar envelope of these stars. And all of these observations are done in the project Atomium. That's why this is here. And so the blue parts we see here is material that is coming towards us, and red parts we see is material floating away from us. And I hope you all agree that these things or these observations all show some structure, some morphology. We can, for example, sometimes this one is just a bit all over the place. In this star we can maybe distinguish sort of a spiral structure. Here in this one we sort of have a bipolar outflow because one part is coming towards us, other material is flowing away. So there's really a lot of different things going on. Now, scientists have, of course, been wondering, also before my time in astronomy, what might be the case or what might be the origin of these structures. And the hypothesis that we're currently take as the correct one is the fact that we think that there are companions present around the HB star. So we have our HB star with the circumstellar envelope, and we suspect that there's a companion that we cannot observe because it's obscured in this circumstellar envelope. And now what happens, of course, if you put two bodies close to each other, the laws of physics say that then the companion will orbit around the HB star. That's very similar than why the Earth is orbiting around the Sun. Now, when the two objects have a similar mass, also the other object will orbit around, and then in total, the two objects will orbit around the center of mass. So now, when this happens in the case we are seeing here, so we have the HB star losing this mass, but also orbiting, this creates a sort of a spiral structure. And here now I show you nicely the image in 2D, but actually this is a 3D process. And so we can look to this 3D image mainly from two sides, from the top and from the edge. And the top view we call face on, and the edge view we call, edge on view. All right. So, okay. We now suspect there are companions present in these circumstellar envelopes. But this raises, of course, a lot of new questions, because before we just assumed the HB stars were alone, that these circumstellar envelopes were nicely spherically symmetric, but now we suspect something else. So this opens a lot of new questions we can research. First of all, what might be the impact of the companions on the circumstellar envelope properties, such as what might be the impact on the mass loss rates or on the expansion velocities, because we suspect that companions can change these parameters. And then, of course, we will have a different circumstellar envelope. Also, the fact that there is a companion present might influence the evolution of the HB star, because as I've told you in the beginning, stars are always evolving. Because of the presence of this companion, this evolution might be different than when the HB star would be alone. Moreover, the fact that there is this companion and there is this spiral structure, which is basically an enhancement in density, this can also affect the chemistry, and in turn, it can affect how much molecules these HB stars give back to the interstellar medium. So it can change the enrichment of the interstellar medium. And the same holds for the elements that the HB star produces, maybe because of this companion. If the mass loss, for example, so this parameter changes, it can also change the amount of new elements that are created inside the HB star due to these nuclear reactions. So it can all change. And so in the end, it can have a big impact also on the life cycle of galaxies. So these are a lot of questions. Of course, I couldn't solve them all. It was also not the plan, luckily. But this opens a lot of new questions, and that's why we're researching now this new hypothesis about the companion being present around these HB stars. Also, there's still another thing. If we look at the planetary nebula, that's also something I mentioned in the beginning. So if you remember correctly, this was the next evolutionary phase of our HB stars. And generally, when we observe these planetary nebula, we see these beautiful images, but the most prominent thing that we see here that's also very asymmetrical, that there is structure presence. So we might think that also these structures are created by a binary companion, but the link is not at all clear up until now. So this is again a question we're trying to solve. Now, how will we solve all these questions? In my case, in my research, we do this using modeling techniques. So we will try to model these circumstellar envelopes. And if we're modeling these envelopes, we need different ingredients. So first of all, here's our system again. So this is the system we're trying to model, the HB star with the companion and its circumstellar envelope. So first of all, we need to model the hydrodynamics, because hydrodynamics will give us density changes. And of course, these spiral structures, as I already mentioned, these are changes in the density. So we need to be able to model this spiral structure using hydrodynamics. On the other side, I also already mentioned there is a lot of astrochemistry present in these outflows. And we also want to be able to predict the amount of molecules present, so the abundances of the molecules. And so these are two important ingredients we want to be able to model in order to model our system here. However, these are not loose from each other. They're connected using by radiation or light. So these can interact via processes with light and also some thermodynamics, which is the exchange of heat and energy. In that way, also chemistry and hydrodynamics can basically interact. So we really need these three elements as a whole in order to model our system. Now, what we want to model in the end is, of course, the observations. So an observation might be like this. So this is an observation of an HB star, LL Pegasi. And so again, the HB star is located here in the very center. And in this case, we see this nice spiral pattern. And we want to be able to model such an observation. Now, actually, what we see in such an observation is molecules that emit light. So again, in order, if we want to model the observations, we need to model the light, because we want to model the emission of molecules. And hence, in order to model this full system, this full observation, we need all of our other ingredients. Otherwise, we won't get to the observation. All right, so if we would have all of these ingredients, we would get this 3D hydrodynamical chemistry radiative model. And I'm already saying this a bit hypothetically because it's still a very much work in process, but that's okay. That's why we do science, right? We don't want to solve everything in one day. And it was also not completely the goal of my PhD. The goal of my PhD is work towards a part of this. So in my research, I worked towards building a 3D hydrodynamical chemistry model. So for now, ignoring the radiation still. And the way I did this is by the three projects that I shortly mentioned in the beginning, and I will now show you in a bit more detail. So in the first project, I did a study of the morphological changes of such an outflow that is perturbed by a companion. So basically, what will change to this outflow if we change our system? I did this using a 3D hydrodynamics code, and so in our system, we have the HB star and the companion. So, as I already mentioned, the research question was, what is the effect on the outflow if we change system parameters? So what might this be? This might be the expansion velocity of our wind. It can be fast or slow in my case. We can change the distance between the HB star and the companion. And lastly, we can change the type of companion. So we can model what will be the effect of a star or of a planet. Let me show you some results. So this works, perfect. Okay, so what do we see here? So it's one of my simulations. In this case, it's a fast wind. We have a white orbit and our companion is another star. And we're looking to the system from the top, so the face-on view. And as you see, we have the HB star here losing the mass. And we also see that the HB star is orbiting itself because the companion is of similar mass. And we see that there is a nice spiral structure creating in this outflow, and this is because the HB star is orbiting. We can also look at the system from the edge. So if we tilt the whole system, then we get this. So I'll let the simulation run a bit. So we already see that there are some arc-like structures being created. So in this case now, the companion is orbiting in front of the HB star. And these arcs are basically the cross section. So if we cut through the spiral arms, we get these arcs. So this also proves that a companion can really create a 3D morphology in the circumstellar envelope. Okay, so this is our basic model for now. We can change the system parameters, as I mentioned. So we'll now go to a slow wind. So here in the corner, you see the previous simulation so that you can compare. So in this case, I think you already see that the global morphology looks a bit different. We still see a nice spiral, but it looks a bit different. So in the center, I don't know if it's quite visible on the screen. So you see that there is actually a double spiral creating. And then globally, we see that it just looks different than what we saw before. And the reason for this is that in this case, the interaction is stronger. And that is because Now the outflow is much slower, and hence the gravity of the companion basically has more time to interact with the outflow. So therefore, because the wind is slower, the gravity can pull harder to the particles to influence their motion. And so we say that the interaction is stronger. Now we will change the distance between the two stars, and then this happens. Oh, sorry, we're first still looking to the edge view of this simulation. I was too fast. Okay, I'll let it run a bit. So we see already that there's again some arc-like structures appearing, but the arcs look different, and especially they're more compressed this time. So this one looks a bit as a spider I always found. But if I let it run along a little bit, you will see that in this x direction, so in this direction, the material will go much further and towards the poles. There's much less material flowing out. So in this case, the whole, yeah, the bulk of the material is compressed closest to the orbital plane. And this is again because of this stronger interaction because the wind is now flowing more slowly. Let us now look at a system where the orbit is smaller. So you already see here that the companion orbits faster around the HB star, and so we're again still in a fast wind. But generally, we again see some different morphologies showing up. Um, Although the wind is still fast in this case, but we placed the HB star and the companion closer together, this also enhances the gravitational force between the two objects. And therefore, also the HB star is orbiting faster as well as a companion, so the interaction is stronger, and hence there is another type of spiral created, a different morphology. We can also look edge onto this system, and then we have this. This is already, voilà, now it starts again. So again, we see like these arc-like structures, so we can conclude these are quite general. It's because that's the cross-section of the spirals, basically. But it's still, yeah, it again looks a bit different because we have a different type of interaction, different, it's now stronger. And you also can see a little bit when it's at the end of the simulation that again, the bulk of the material is compressed slightly towards the orbital plane. So that happens when the interaction is stronger. Now, finally, we can look at a simulation where we place a planet around the companion instead of a star. So this is what we get. So I think you already noticed that the spiral, it's even barely visible on this projector screen. So it's much less distinct. And this is because, of course, a planet is much less massive than a star, and hence the interaction is less strong. And also something that is prominent here is that we see that now the HB star really stands still because, of course, it's the companion is not massive enough to also let it orbit. If we also tilt this simulation, I think this might be very hard to see on this projector screen, but there's only slight blobs of material basically in the x direction that are flowing away because of this spiral structure. So when there is a companion that is of planetary type, we can conclude, because the interaction is less strong, that the outflow resembles better a spherically symmetric object. All right, so we've seen a bunch of different morphologies now, and in this research, I found that we can actually classify these via a certain parameter, which we called epsilon. So there's a few equations here now, but don't worry, you don't have to understand them. So this epsilon parameter, it gives the ratio of the energy density of the gravity of the companion to the kinetic energy of the wind. So it's a sort of measure of the strongness of the energies. So we can calculate it for all of my models. So here on the x-axis, you just see my models listed, and you can see their value. And I filled the symbols according to going from simple when they're empty to quite complex when they're completely full. So I mentioned the formula. Don't worry about this. So what's important that within this parameter, we find the wind velocity, the orbital separation, which is this A, and also the mass of the companion. And these were the three parameters that I changed during my simulations. And therefore, also this parameter, this epsilon parameter, can really distinguish between the different morphologies. So we found that so when this epsilon value turns out to be low, when we calculate it just from the parameters of the system without running a simulation, we will expect something that's quasi-spherically symmetric, like the one with the planets. Now, if we calculate the value is around 1, we can expect like a nice spiral, such as the first simulation. And then when this epsilon value is larger than 1 or even very large, we can expect that this, if we run the simulation, is quite complex. All right, let me recap that a little bit so everyone stays up to date and can still follow. So we now know that companions, when they are present in these circumstellar envelopes, that they can perturb the outflow. And by perturbation, I mean that they can create density enhancements in the form of these spirals. And it's not just one type of spiral we find a lot of different morphologies. So then the next thing what we're wondering about is, will this affect the chemistry? Because we know chemistry heavily depends on density and temperature, for example. So in a second project, I tried to study this via a sensitivity study of the circumstellar envelope, chemistry that goes on inside the circumstellar envelope. So in this time, I use only one-dimensional models, a chemical kinetics model, and we do not include the companion. And the reason for this is quite simple. It's just because this model does not exist. So we don't have a 3D chemistry model where we can include the companion yet, hence the research. All right, so let us look again at the system. So we have our HB star and the outflow. In this case, we will look radially outwards, so just in one dimension, and we'll assume that we have a smooth outflow. So by this, we mean that closer to the HB star, we have a higher density and a higher temperature, and when we go outwards, the density and the temperature will drop. So it's a little bit like this color scheme. Not quantitatively, but to give you a feeling of how it might look. And we're looking at a certain part in the out. So we start about 10 times 10 times the size of the HB star outwards. And in our simulation, at this point, we inject some parent species, as we call them. So parent species are just a set of molecules that we assume have formed at this point in the outflow. So everything that goes on before, it's quite complex. We do not take it into account. We just know that at this point we have about 10 molecules that are present there. And then we evolve what happens to these molecules when we go outwards in the outflow. And we only take into account gas phase molecules. Now, how will these molecules interact? Because if it's just some molecules that don't interact with each other, it's quite boring chemistry. So there's another crucial factor, which is namely radiation. So outside of our circumstellar envelope, there are, of course, other stars, and all of these stars shine light, and also partially in the ultraviolet part of the electromagnetic spectrum. And UV radiation can break up molecules, basically. And so first, it can penetrate the outflow from outside, and it will break up our parent species. And then there's all kinds of radicals forming, and then there is like a big cascade of chemical reactions going on where different molecules are forming and interacting. And this is basically what we're trying to model with this model. Aha, I almost forgot that we're researching something. So what we're trying to find out in this, or what I was trying to find out in this project, was what is the effect of a different temperature. So for example, we can have a higher density or a lower density, and the same holds for the temperature. We can also have a higher temperature or a lower temperature in the outflow. So let me now go over to the results. I was already about to show the results before the question was there. Okay, so what do we see here? We see a graph of the chemistry. And so our HB star is just slightly outside of this graph. And we're looking radially outwards in our outflow. And we start with this molecule here. So C2H2, it's a parent species. And we can see that because it's present in the beginning of our outflow. When we go outwards, at some point it drops. And the reason for this drop is because there is UV radiation hitting the parent species and therefore breaking it up. And hence, the daughter species, as we call it in astrochemistry, is created. And as you can see, there is one hydrogen gone because of this radiation. So we can see indeed where the parent is broken up. There is at some time or at some moment in the outflow, we have this daughter species created. But again, the daughter is also destroyed because of radiation. Now, if we lower the density of this outflow, we get this effect. So we see that for a lower density, the radiation can penetrate much deeper into this outflow, and hence the parent species is already destroyed much earlier on, and therefore also the daughter is created earlier on in the outflow and also destroyed earlier on. So that's the effect of density. So when we lower the density, everything is broken up earlier or closer to the HB star. Now we're also looking at the effect of temperature. So if we also add outflows with a different temperature to this graph, it looks something like this. So there's a lot of colors here. But basically every color is also just one line for an outflow with a different temperature. And the red lines are outflows with a higher temperature, and the blue lines are outflows with a cooler temperature. And so what happens here, we can already observe here that when the outflow is warm, the parent species and also the daughter, they exist much later in the outflow. And the reason for this is the following. So we also have a back reaction to say. So when the parent species is broken up, it creates a daughter. It can also recreate the parent species by catching molecular hydrogen. However, it cannot always do this because there is an energy barrier present in this reaction. So this means that the reaction can only exist if there is enough energy left to cross this energy barrier, or in other words, if the temperature is high enough. So what happens for these warmer outflows? Also, first, the parent is destroyed to the daughter, but because energy is still high enough, because we have enough warmth, basically, we can recreate the parent. And then, of course, at some point, I already told you, when we go outwards in the outflow, temperatures drop. So also at some point, radiation will take over and the parent species won't be created again. All right, that was a whole explanation. We see a similar effect, for example, in water and its daughter species, OH. And actually, OH is a very important molecule because it can also interact with a lot of other molecules, for example, with CO2 and CO. And now we know that this OH molecule is depending on the temperature, and hence it can actually make other species also dependent on temperature. So what we see here, so we have CO2, I mean. This can also be broken up by radiation to form CO. But if CO catches OH, it can reform CO2, and therefore we also have this temperature dependent in the CO2 species. So this means that if there's already one molecule basically dependent on the temperature on the or the density, it will influence the whole chemical network and influence the abundances of all the other molecules in the network. So we see that changes in the temperature and the density really affect the chemistry. So I was actually already telling you a bit of recap. So now we've seen that we get these density enhancements and also temperature enhancements. We've seen it in the hydrodynamical simulations. We now saw from the chemical simulation that if this would happen, our abundances will really change. So therefore, we proved sort of that there is really a need to combine these two ingredients. So we really need a 3D hydrochemical model. Now, of course, every time when you have a great idea, there is something stopping you. So in this case, these hydrodynamical models that I've shown you in some GIFs, they actually take quite a lot of time to calculate. So they take about, I don't know, weeks or even months they can take. And if we would also add our chemical calculations on top of these models, it will just become too slow and it will take us too long to compute such a combined model in a feasible time. So therefore, we need to take an alternative approach. And this alternative approach, we will mainly try to make something different of this chemical model. So therefore, I introduce you to Maes, which stands for Machine Learning Approach to Chemistry Emulation. So we will find something else basically to do the calculations of the chemistry. So now, how does chemistry usually work? We have some input values, mainly the density, temperature, and radiation field. So that's the physical parameters. And then we also have our chemical parameters, which are the abundances of all the molecules, so the amount of molecules present. Usually, we can put these parameters into a chemical kinetics model, and what comes out is an updated version of the amount of molecules. So we know how many of every molecule is present after a certain amount of time, delta T. Now, what we aim to do with Maes, oh, sorry, I forgot this. So what is chemical kinetics? In basic terms, we can track the change in a certain species over time. So that's this side of the equation by just balancing out how much is produced and how much is destroyed. So if we take, for example, water, we know how much water we have over time if we know how much water is produced and how much water is destroyed. So that's how chemical kinetics works. But of course, if we have like 500 molecules, it's quite a lot of equations that we need to solve. So therefore, we want to go to an alternative way. And that alternative way is a surrogate model. So it's basically a completely new model, but we aim that the model is able to do the same thing, but without all of these calculations. So we'll still aim to take the same input, put it through our new model, and produce the same outputs. And of course, from this title, uh, you already guessed how we are trying to do this. It's with machine learning and artificial neural networks. So this is a very basic schematic form of an artificial neural network. And of course, a big aim to do this, to build this surrogate model, is to gain a speed up in the chemical calculations. So if the surrogate model is not faster than our classical way, then it's not useful to take the alternative approach. Okay, so with this in mind, we developed Maes, and because it's with machine learning and everything, it goes together with a certain architecture. So we start from our input, which I already introduced. So we have our 3 physical parameters, and we have a bunch of molecules, and in our case, it's about 500. Now it's quite a large input parameter space. So what we first do is encode this input space to a much smaller set of parameters, to about eight parameters. So it's quite a difference. Once we have these 8 parameters, we can evolve. Ooh, sorry, I forgot again. So what's actually in this encoder is a neural network. And so we can train this neural network in order to produce these 8 parameters. All right, so once we have our 8 parameters, we can evolve them over time. So we have given a certain amount of time, we can evolve the 8 parameters, and we can predict these 8 parameters a time delta t later. Of course, these random parameters, because it's just a mathematical representation, we don't really know how to handle them, so we will decode them again first. Again, the decoder, now I was too quick. The decoder contains another neural network. And once we decoded these 8 parameters, we can predict how these molecules or how much of these molecules are present at a time later. So that's the architecture of Maes. Now, it's a very nice theory if I tell you it like this, but of course, it only works when we train it. So how does this work? So we have our architecture, we can give an input to the architecture, it gives us a prediction, and we need to then compare the prediction to our classical models that I've shown you before in order to see if the architecture works. Of course, if we only show it one prediction, it won't work, so we'll just give it a lot of inputs. I think it was about 10,000 inputs I trained this thing on. So we just repeat the whole process with different inputs up until the point where we are satisfied with our prediction, because at that point our prediction looks more or less like what we want to, like the classical models, and that's what we're aiming for. Okay, so this brings me to some results of Maes. So what you can see here, it's quite different, quite the same as we've seen before. So again, our HB star is located slightly outside of our graph, and we look in radially outwards in 1D in this outflow. And these lines again show the amount of certain species present, and here I list the species. Doesn't really matter which molecules, but just to show you a bunch. And now these dashed lines are still the classical model. So it's not yet Maes, it's only the classical model. And now I'll show you what Maes predicts. So Maes predicts this, and I hope you agree with me that it's quite a good match. And we were very happy with the result, of course. And you can also see from the errors, so sometimes it's not perfect, but that's how it goes. And we can probably train further this model in order to have a better match. But this is already a very good first match. And I hope you also recognize these lines now. So that was the inspiration for the cover. Now, I also mentioned just earlier that there was one important thing that needed to be true for the surrogate model, which is that it needed to be faster. And we found that Maes was able to make these predictions, so the full lines, in only 5% of the calculation time that the classical model needed. So it's already quite a speed up. We aim higher still, but that won't be for me. That's for people that follow me. But this is already very good first result, and we were very happy about this. So this already brings me to my conclusions of this presentation. So I've shown you that we've seen a lot of different morphologies due to the presence of companions inside these circumstellar envelopes. That was the first part. On the other hand, we saw that chemistry will change if we change the density and the temperature in the outflow. So this makes that if we combine these 2 points, we will really get a different result for a certain outflow when a companion is present. Now, lastly, I proved with this research that it is possible to build a surrogate model that is faster and gives good results for the chemistry, which we here called Maes. Now, of course, research never ends, although for me it does here today, but there is still a lot of future work that can be done, and hopefully, I hope my collaborators will continue this work. So first, of course, now that Maes exists, it can be coupled to the 3D hydrodynamics so that we can really build this 3D hydrochemical model. But it's not done there. I also already mentioned somewhere in my introduction that we also need the radiation. So this is also an important aspect. We need to couple to the hydro and the chemistry to in the end come to a comprehensive model that can really model the whole circumstellar envelope. And of course, we want to do this all in 3 dimensions because these objects are in 3 dimensions. There's a lot of steps to take. I won't go into detail, but we're not there yet, but we're working towards it, and it's looking very promising. So once we have this model, we can finally start predicting correctly all the different parameters of the circumstellar envelopes. For example, we can see if our mass loss rates were correct that we got from observations. We can look again to the chemical yield, so how much of the molecules is left over from the HB stars, basically. Also, we can check if there changes something for the amount of elements that are produced inside of the HB stars. So in the end, we can hopefully better predict the evolution of the galaxy, or at least the part where HB stars contribute. So with this, I thank you all for listening to my presentation. Of course, I want to thank my examination committee also for the interesting discussions during my internal defense. And of course, all of this research was not possible without my collaborators. And Jolien, I just said to you that you're a doctor. Thanks to Mats. So thank you all to my collaborations. And I hope now all of you here that you know why I chose these lines on my cover of my thesis. So thank you.
Thank you, Silke, for the very clear presentation. Let me introduce you the members of the examination committee. And I will start with the supervisors of the work, so the promoter, Professor Lynn Dessin from KU Leuven, and her colleagues, the co-supervisors, Dr. Marie van de Zante from the Leiden University in the Netherlands, and Dr. Frederik de Koster from our university. As Silke has mentioned already, a couple of months back, we had already an internal defense, and several members have attended this defense. Of course, few of them were not able to join us today, but I would like to introduce them to you. And these are Professor Connie Arts from our university, Dr. Jan Bolte from Kiel University, and Dr. Serena Vitti from the Leiden University in the Netherlands. Professor Jeremy Yates from the University College of London is joining us today online. And then we have our colleagues in the examination committee present here, and that's Dr. Pablo Heise, also from the KU Leuven. And I hope I'm not forgetting anyone. As you can see, it's a fairly large committee. And myself, I'm Carmen Bartik, also from the Department of Physics and Astronomy, and I'm chairing this session today. So with that, I would like to invite Professor Yates to start discussing the work of Silke, or making remarks or sharing some comments on the work. So please go ahead, Professor Yates.
Thank you very much. So I'd like to congratulate Silke for an excellent presentation and groundbreaking work. I think that should be acknowledged straight away. Physically informed neural networks in these complex situations are very, very difficult to get right. And I think we ought to congratulate you on that and recognize the ingenuity and skill by which you did this. Just a couple of what I hoped are simple questions. There are going to be uncertainties in your simulations.
Yes.
do you have a feel for what they are and how big they are?
So do you mean the uncertainties on the real models or on the surrogate model?
Let's just do the surrogate.
Okay,
let's,
this may be more difficult.
yeah,
So
yeah.
yeah, so of course the surrogate model has probably even larger uncertainties than the real models do, although models are always uncertain, so we need to be careful with that.
Mhm.
And there are ways to come to a sort of uncertainty on the whole surrogate model. So yeah, we train it on a bunch of real models, which in this case we take as true. And there exists different techniques to build in sort of an uncertainty propagation through the training. I should be honest that I don't know these by heart, but I have been discussing this earlier also with Frederick throughout the whole development of our Maes model. But it is indeed something very important we should take into account and shouldn't forget about it to also maybe as a next step try to propagate some uncertainties through these models. So for the moment, because you also asked if I have a feel for the size of the uncertainties. So yeah, I don't really have a feel for that. I think it mainly depends on how big the uncertainties are on the real model. If we would incorporate these, we can also propagate it through the surrogate model.
Okay, thank you very much. So you talked about at the end the need to integrate with the hydro model and a radiative model.
Yes. Yes.
Do you ever see where the entire 3D hydro radiative chemistry model is itself a physically informed neural network?
Sorry, can you repeat the question? Can I see how the
Can you see if it would be desirable? So if yeah.
Yeah, so yeah, the whole the comprehensive model, as I've called it, it's indeed including hydrodynamics, chemistry, and radiation. So if we would continue with Maes, the chemistry part would be physically informed. I don't know if we already settled on an idea with the radiation part, because of course we have this code Magritte that you know of. We might be able to use that, but it's also in itself a slow code. So we maybe also need to go to some machine learning options there, or maybe strip it and only use essential parts that we need in our comprehensive model.
Okay. Right, I think that's it from me.
Thank you.
Thank you.
Thank you very much, Professor Yates. So I would now like to give the word to my colleague, Dr. Pablo.
Hello. Hey.
Hey.
Thank you very much. Very nice presentation. I totally agree with Jeremy on that. I have mostly questions about your journey on neural networks.
Yes, I expected that.
Which I guess you enjoy because it's on your cover now.
Yeah, it's a nice result.
So Jeremy already asked about the uncertainty.
Yes.
So there is one part which is the uncertainty on your model.
Yes.
Which, for example, you could do something like an ensemble of models. I think you already explored running on with different seeds.
Yes, I did that after. Yeah, what
so
you
with
asked
that,
after
you have already a distribution of predictions.
That's true. Yeah.
Which you can compute standard deviation and so
yeah,
on.
That's true.
But I wonder on the uncertainty that's on the prediction, but in this case, you also have uncertainty on the ground truth that you are giving to the model on the labels.
That's true.
Do you know that? If you know that, can you use it?
So that's actually a very good question. It's something that I didn't touch upon now in the presentation because it would take me a bit too far and given the time. But so on the chemistry side, we know that there are big uncertainties on the chemistry, but usually observational people or even in the modeling world of astrochemistry, they don't usually state these uncertainties because they're not really known. And within my research about the chemistry, I tried to do a sensitivity analysis where indeed I changed the density and the temperature. And then we saw that, for example, for parent species, we can quantify a certain envelope size, so the point up until where they are photodissociated. And by changing the density and the temperature, we also saw that, of course, the envelope sizes of the different parent species changed. And from that, we sort of try to make a figure where we include all of this information so that, for example, on the observational side, when you know the mass loss rates and the expansion velocity of your outflow, you can go look in that figure, and then there you would be able to see indeed that there is a certain range on the envelope size. So in a sort of, yeah, not really very, yeah, so we try to make to quantify the uncertainties indeed on these envelopes, but of course it's still just by different models, and then the model that we used, there's already also uncertainties because it contains reaction rates of chemistry, and on that there's again another uncertainty. So from all sides there's different uncertainties. So at some point you need to take something as the ground truth and then propagate it in that way. But I've looked into that a little bit. If we take these chemical rates basically as the ground truth, so that we take that people that measured the chemical reactions, if we state that as true, then we sort of calculated the uncertainty on, for example, these envelope sizes. But you can also do it the other way around, and that's something that Marie is working on.
And if you can estimate it, you can add it to the loss function, and there, I mean, it will propagate also to the model.
Yes, probably, yes.
So in the last plot where you show the abundances of the species,
yes.
So some of them have a bit more error than others.
Yes.
And we already know that the ground truth is not perfect.
Yeah,
so,
that's true.
I mean, we shouldn't aim to match it perfectly,
no,
right?
I agree.
But are there perhaps any of the species that you know for sure that are very correct and that you should follow perfectly, or perhaps zones, I mean, different radius that you should match?
Yeah, so there's definitely some molecular species that we know more about. So for example, CO, which is the upper one here, the darkest color. And this is, as you can also see, it's very abundant. And that's also something we see in observations. So I think for CO, we have a quite correct estimate of where this drop-off would be. And indeed, it's now, in this case, also a molecule that has the largest error when it's predicted by Maes. So we would be able to maybe use these this information from observations to match better certain molecules. That might be a very interesting follow-up study, instead of just trying to match everything sort of properly. Maybe try to match the more abundant ones even better. But there's also some chemical species that we already know that in models and observations are quite different. Now I didn't include it here, but I think SIS is such a molecule that predictions are not at all close to what we observe. So there's also still a bit of missing chemistry knowledge, basically. But it would be a good approach to match better some important molecules.
Okay, perfect. And now a question about the model that you use for the latent ODE.
Yes.
So in general practice, in neural networks, the latent ODE is it's a small neural network, like a 3-layer, something like that.
Yes.
But in this case, I remember that you used you fixed a particular structure for the equation.
Yes,
having
that's
a
true.
constant term, linear term, and then the cross products.
Yes.
So why that choice? What not leave it like completely flexible, like in the crazy neural network guys?
So maybe shortly for the public, this green, sorry, it was the English. This green oval shape, there's a lot of mathematics behind it in the real deal. So indeed, as Pablo Huizens here talking about. So for this green oval, we've chosen a specific equation, which looks like the equation that's actually, okay, I shouldn't go back all the way. That's similar to like the chemistry equation that I schematically showed a little bit. But actually, we could also have just chosen another completely other function, or even indeed no function at all, as you're stating, just a complex neural network. So initially, we went to something that we're familiar with, so something that looks like the chemistry that we know. But you also mentioned it during the internal defense that we could have gone crazy, and maybe that something else works even much better than something we're familiar
with. It seems to me that perhaps it's a bit too much of a restriction, because these are not abundances anymore. I mean, what goes out of the encoder.
That's true. I agree. These 8 parameters, or about 8 parameters we have left, it's not chemistry anymore. So maybe indeed we made a mistake there, but it still turned out pretty well for now.
Well,
But
yeah, I
that
mean,
would
there's
also again be a very
room for
important
improvement,
follow-up.
of
Yeah,
course.
exactly, room for improvement.
And regarding the relation between these 8 parameters and your input,
Yes.
did you have, by any chance, try to decode a bit how the different species are related to each of these 8 parameters?
So we haven't looked into the relation between the parameters here in the latent space and the input, but we have tried different sizes of latent space. And so I think 8 was the minimum. We also took 16 and 32. And there we saw that actually even with a small latent space, given there was a shorter training time and an equal error at the end, we found that this works already pretty well. But indeed, it would also be very interesting to really find some correlation or look into the structure of this latent space to maybe get to know better this whole architecture and then also improve on that side.
Yes, I mean, try to understand perhaps what the species are being omitted by the
Yeah, for
network and stuff
example,
like that.
because we know indeed from the classical chemistry that it's like about 10 molecules that are very important and all the other 400, so many are not quite significant. So that would also be very interesting.
Yeah. Thank you very much.
Thank you.
Yes.
Thank you, Dr. Heze. So maybe before going to the supervisors, I will ask you some questions from Professor Koniarts.
Yeah, yes.
That was also very much interested in uncertainties.
Yes.
And she's a bit more specific. Well, she's somewhat more specific. So she says, what is the importance of each object having its own initial helium abundance at birth, rather than the one value that you fix now? Given that the total mass fraction must be 1, a different helium mass fraction will impact the hydrogen mass fraction, and this will propagate into the formation of the molecules in the wind. How important is this with respect to other physical and chemical uncertainties, effects that for which you make assumptions?
Okay, so I think Connie Aert, maybe she is listening online or maybe she'll listen afterwards to this. It's also questions you ask her in the internal defense. So maybe to inform the public a little bit. So when we have these molecules, of course, we need to first state how much hydrogen is there, how much helium, and then basically in astronomy we say and the rest, which is all the other molecules or all the other elements. And indeed, we know for certain stars, the amount of hydrogen can very much change. But I think in the case of HB stars, the amount of surface helium. Sorry, I made a mistake before. So we're talking about helium. So the amount of helium for HB stars at the surface, I think it's quite general. And in this case, we took the amount of also what we find for the sun. But it is true that if we would change this amount of helium, that we also would have much less of the other species. So hydrogen, we would still have a lot, but there's also a lot of carbon, oxygen, silicium, sulfur that interact. And I would suspect, like carbon is a very big driver of chemistry, that and if there's less carbon, that there would also just be less chemical reactions in general, and of course all the species that do contain these other elements will be very less abundant, and the outflow would again look very different if you look at the chemistry.
All right. And some general questions. She would like to hear your reflections about those. So where should one put most effort in the future? In better chemistry models or in better emulation?
Ooh, that's a very good question. I have not thought about this. Yeah, so there is a need to improve the chemistry models, and that's something also my co-supervisor Marie has been doing. So trying to step by step also incorporate like structure inside of these 1D outflows, and also putting a sort of a companion in there, and that already gives us a lot of interesting results. But still, if we want to go to the full 3D model, we know that this is not possible with the classical chemical calculations because it will just take too long. So I think my opinion would be to put a bit more effort now on the emulation side, work further on Maes. I should also promote, of course, Maes. And in that sense, hopefully, once we couple it to the 3D hydrodynamics, we can in that way also improve on the chemistry so that when there's a companion present, also in the end, the chemistry will resemble the observations. So I think the way forward for this particular case is using emulation.
Okay. I think she has a somewhat opposite opinion.
I
She
guess so.
thinks,
Yeah.
well, she said that actually, if you would develop better chemistry models, then probably you have to redevelop and reoptimize your emulation.
That's also true.
But yeah,
That's very true. No, yeah, there's also training and retraining. It's a difficult
it's
balance.
a trade-off.
Yeah, exactly.
Yeah.
It's a trade-off. That's exactly true.
All right. Good. So let's move now to the co-supervisor. So maybe Frederick first.
Thank you very much. Thank you, Silke, for the beautiful presentation with beautiful slides. First, perhaps a question for the audience. I also asked it last week, so
Oh.
probably know what
I
is
should
coming.
prepared.
Aha. So you've shown beautiful movies of stellar winds evolving, but what are you actually showing there? So what do we see?
All right.
You made it all look very simple, but there's a lot of complexity hiding between these movies. Can you elaborate on that complexity?
Yes. Okay, so indeed, Jolene got the same question last week. I don't remember exactly what she answered. So what we're looking at here, no, not in that sense, in the sense that there was a lot going on. Okay, so what we're looking at here, so it's a slice, first of all. So we made a 3D simulation, and in this case, the hydrodynamics is made from particles. So it's a particle-based hydrodynamics code where there's basically, so we start from our HB star, and every time there is a shell of particles launched, that's the word I was looking for, launched from the surface. And then all of these particles just go outwards. Now, as you can see in the simulation, we don't see particles, we just see a very nice, smooth image. And this is because in these particle-based hydrodynamics codes, the properties of the particles, so the density and the temperature, they're all smoothened out over a certain radius. So in this way, the different particles can actually interact with each other. So then what we're looking at here is then a slice to such a 3D. So basically, in this case, it's the slice that's darker here through the model where all the properties are smoothed out a bit. So that's why we don't see the particles anymore, but we still see the nice spiral pattern.
Okay, thank you very much. Also, in your chemistry models, there is a lot of complexity that you've nicely hidden away between nice figures.
Yes.
And you already had a few questions about uncertainties, but what actually are the key input parameters to these chemistry models that are causing the uncertainties in your models, and why are they uncertain?
So there's different kinds of input parameters that can cause uncertainties. So in my case, I'm gonna just skip a bit further. So in my case, the uncertainties that we try to quantify are the uncertainties on the fact that we cannot exactly predict the density, the temperature better, but the density of an outflow. So when we observe an HB star and its circumstellar envelope, it's very hard to exactly predict the density of the circumstellar envelope. So of course, this then has an uncertainty on it, and it will influence the amount of species. But on the other hand, we also have just the chemistry. That's what someone asked before. Just in general, chemical reactions, they all go via a reaction rate, and also there's a lot of uncertainty. So it's a really different type of uncertainties that go into the model. But in my case, we took the chemistry as the truth, and it's mainly that the density from an observation is very hard to quantify.
And how many reaction rates do you have on average in this model?
So in this case, we have a reaction network of about 500 species, and this means that we have about 6,000 reactions.
So that's 6,000
uncertainties.
inputs of uncertainties.
Yes.
Yes. So that was the thing I
Okay, so that's what I
was kind of after.
So lots of uncertainty.
Thank you very much. Let's see. Okay. So you very briefly mentioned the training, but I think
Yes.
the audience seems very smart. Can you try to explain what it actually means, training, or go a little bit more deeper into what it actually is? So what does it mean to train? Or do you go to school with the model, or how? What do
On the
you
1st of
actually
September,
mean?
earlier this week. No, so indeed, that's a good question. So I here show you some blank figures or like shapes, but inside of the, maybe it's better to show this. So inside the encoder, the evolution part, and the decoder, so the encoder and the decoder, it contains some neural networks. But of course, what's a neural network? There's a lot of free parameters there. So when we initialize these parameters, they're just set to a random number. But in the end, when we finish the training, we hope that all of these numbers are the right ones, in order that if we put a model, or like an input in the input side, that when it comes out, it's the correct prediction. So all of these free parameters along the way, so in the encoder there are free parameters, in the evolution part there are free parameters, and also in the decoder, all of these free parameters need to be set right. And every time when we train a model, these parameters are changed in a certain way because of mathematics and smart people that invented the whole training flow. So every time we show a model basically to this architecture, the free parameters change a little bit so that the prediction becomes better. But if we show it multiple good models, and with multiple I mean 10,000s of more, then all the free parameters will change to their best value in order to make good predictions.
Do you have an idea of the number of how many free parameters there are?
Oh, I should have an idea, right? I wrote it down in my thesis, but it was about the order of 100,000 or maybe a million. I don't, orders of magnitudes.
I don't know.
Yeah, it's somewhere in the footnote in the thesis, but I forgot the real number. But it's quite, it's about 100,000 or like a multiple of 100,000, I think, depending on which model, because we,
thank you,
played around.
And then perhaps, so you said you had a 20-fold speed up on average now with Maes.
Yes.
But how much faster do you want it to be? It doesn't, well,
Yes.
Where is the goal?
Yes, so this 5%, if we flip it around the number, we get about speed up of 24 indeed. We want it to be still quicker. We hoped rather for like 100 times faster or even 1,000 times faster. We're not there yet, but as already by the questions of the jury, there is still a lot of room for improvement, also on the emulation side, maybe also still on the physical side. But also there's a lot of promise when we can finally put Maes or link Maes to the 3D hydrodynamics, because all of these emulation models, there's a lot of matrix computations going on, and we can very efficiently do these matrix computations. And also when we can connect Maes to the hydrodynamic models, as you also already asked, we're working with particles, and we can actually, all of these individual particles, if we would do classical chemistry, we would take a particle and calculate its chemistry and go on. So it's always a separate calculation. But with this machine learning approach, we can use this efficient matrix computation where we just take all the particles, put them through our model once, and then we have the results. So this, we've not tested it yet, but this promises to even have another factor of 10 speed up or hopefully higher, and then we're close to the 100 or 1,000 times faster.
And where does this 100 or 1,000 come from? Is that because we like it, or?
That's a good question. We've discussed this before, and I should be honest that I forgot the reasoning behind it, but there was a reasoning behind it why we would get to even a factor 100 or 10 or 100 more. But I would say it depends on the amount of particles we have present in our simulation, and the amount of particles in these hydro simulations is also like 1 million. And of course, we won't get 1 million times the speed up if we only need to do the model once. There will be some, I was going to say delay, but that's not the correct word, but there will be some downsides still. But there will be a significant speed up. I think that's what we agreed on.
Yeah. Thank you very much. We'll discuss later. Perfect.
Okay, thank you very much. So, Dr. Van der Sande.
Thank you, Silke, for the very nice and very beautiful presentation. It was very clear. I have a few questions, not too many. Well, Frederik actually already asked, because I'm also very interested in the maximal speed up with Maes, but you already answered that question. So I'll go back to your hydro models, because you showed the effects of having a planet versus a star within your outflow, but these planets and stars don't radiate in your hydrodynamical model. So what do you expect would be the effects of including radiation in a more general way?
Yeah, so indeed, in this case, it's only hydrodynamics. And as I mentioned, there is still chemistry and radiation missing. And other research groups outside of the KU Leuven have included radiation, and I think their results showed that because of radiation and because the star shines, of course, when matter is present, the radiation won't shine through all the matter. So depending on, for example, I'm gonna skip to the other model. So if you remember this model, the interaction was stronger, and especially when we looked at the edge of this model, we saw that the material was much more compressed towards the orbital plane. And I think the study where they included radiation even saw that this effect was enhanced, because then there's more material present in a certain range. So hence, if the star shines, it's harder for the radiation to go through this material if it's more. So, and then this accumulates, and even the region, so the region here in the x-axis will even become more dense. I think that was one of the predictions they made. So yeah, probably, hopefully, we will get that too in order to see if we get similar results. It's always important in science to get similar results.
Right. Yeah. Thank you. And then maybe talking about a one-dimensional chemical
Yes.
model.
Yes.
So you say that you start at 10 AU, so not at the stellar surface. Then you mentioned like, oh yeah, the inner winds, there's a lot going on.
Yes.
Which, fair enough, that's why we don't include it. But you do make some implicit assumptions about everything that happens within the inner winds because of the the initial abundances, etc. At the start of your model. So what exactly do you assume that has happened in the inner wind when you start your chemical model?
It's a very good question, and I'm not really thinking very hard. Okay, so indeed, we're talking about this part. It's now hard with that red laser lights in the red region. So there's a lot of, so the dust that I talked about in earlier slides. So there was this dust production that created the whole outflow. So dust is an important aspect that we assume was there, and that dust had formed. So that's something that goes in there. There was dust formation. We also assume that there is no chemical equilibrium at that point. And because if it was in chemical equilibrium, it was quite easy, but because we have this outflow and expansion, all of the chemistry is taking out of chemical equilibrium. So I think that's another assumption that goes into that region. That's the things I can really think about now. There's probably more that you will inform me on later, but that's what I'm coming up with now.
Yeah, no, you're right. You're right. And then maybe a final question again about Maes. So we've been talking a lot about uncertainties, but can you tell me a bit on how we can test the predictions of Maes? Both, just we can take all the uncertainties into account, but how can we test the model predictions? Do you think?
That's a good question. That's something also we've been discussing about. So it's with Maes, somewhere in the audience, we were thinking about this. How can we test it? So our next step would be to really couple Maes to the 3D hydrodynamics. And again, we can make some assumptions okay, that's a bit weird to say, but first go back to Wendy again and then calculate indeed a hydrochemical model, but using Maes. And for a small set of models, we can do that also with a classical model. But because I've been telling, the classical model is much too slow to really do a big study. But if we only for a few cases, we can still do it. It's feasible. And if we do it for Maes and also for the classical one, we can really combine these two and benchmark a little bit if Maes works, because now indeed it's only on like this 1D radius as it's still shown here. But we want to also test it on the 3D hydrodynamics. So we can do that first using a classical model on only one hydro model to benchmark that one with Maes.
Right, yeah, nice. Thank you. And I'll give the...
And now I'd like to invite the promoter, so Professor Dessin.
Thank you, Chairman. Silke, thanks a lot for this very nice presentation. I have seen many new slides today, which I really welcome. You know, it was a very good way to present your work, a work that has been excellent, as has been said already a few times today.
Thank you.
I had a question on the parent species, but Dr. Van der Zande was already pointing towards that. So, but there was also another question that came to my mind when I was listening to your presentation. Since you have been showing us, or to the audience at least, also this table of Mendeleev by Kobayashi. So maybe can you show it again?
Yes, let's go pick all my slides.
I know. Sorry for
That's
that.
fine. Okay,
Yes,
so
here it is.
I'll leave up some of the
Can you
annotations.
maybe explain to the audience what is on the x-axis and what is on the y-axis?
Oh, that's, I should have looked into this more. Okay, so I suspected on, so what Professor De Sine is talking about. So if you just take one box, you can actually draw axes on the left side and on the bottom side. And I think the left side, so the y-axis, it's pretty straightforward. It's just the production of, or the amount of that element that is present. And I think, but I'm not sure about this, that the x-axis on every box is age, or like age of the universe. That, for example, yeah, I think it's age. I was about to give an example, but I don't know specifically which one. But I think that's on the axis, but I'm not exactly sure.
Which is correct. But then, why is the y-axis so different for each of these? They don't seem to be all going to one, so normalized units. So you see, if you look to number 79, for instance, it goes only up slowly. So it doesn't reach one when it would have been normalized units, while other ones seem to go to one. So is that then something random, or how should I interpret that?
That's a very good observation, and I should be honest, I haven't looked into too much of what the colors exactly mean and what the axis means. So I'm not sure about the normalized
That's
units
all
and
fine.
stuff.
Let's look into that.
I can
Okay.
still do it afterwards tomorrow.
Thanks a lot.
Thank you.
All right, so this is a public defense. So now I would like to ask, or to invite the audience to ask questions. You have now the opportunity to ask Silke something about her work. Someone? Yes, there in the back. Shall I give you the microphone?
Thank you. So thank you for this very interesting presentation. I finally understand a little bit what you were doing next to me this whole time. But so I seem to see in some of these hydrodynamical simulations some shock fronts. And,
Yes.
so I was wondering what type of interaction, chemical and dynamical interaction happen inside these shocks, and like, is that part of the things that you were looking into?
Okay, so it's a good question. So these shock fronts that Romain is talking about, it's yeah, I should be able to zoom in now to show them better. And I should also be honest, that's something I didn't look into too much. It's mainly the global structure that I looked into, but I think these shocks are just, they faster material at some point meeting slower material, and hence if fast material meets slow material, there is a shock front created. So it's quite a dynamical shock. Yeah, it's quite a dynamical shock, and there's probably lots of other types of shocks present, but I'm also not sure if we can model it with this type of hydrodynamical code. Okay. So it's fast material meeting up with slower material.
Okay, thank you.
Other questions?
I will ask a very simple question. Did you enjoy your 4 years? And why do you stop?
Okay, that's not a question I expect. So that was my father. So you should read my acknowledgements in my book later. No, I really I enjoyed the 4 years. Of course, it was not always easy. Also on the research side and sometimes on the motivation side. But in general, I'm very proud of the things I did that I showed here. There was also a very nice collaboration with the colleagues here, and also outside of the colleagues I collaborated with, there's also very nice people around. Yeah, and then probably why do I quit with this? That's a hard question. I think the academic world, it's not for everyone. It's a hard world. You need to sacrifice some things that I maybe don't want to sacrifice. And I also, astronomy is very nice, and it's very interesting, and all the physics behind it, I very love it. I very love it much. But it's also very far from us, and also in a very literal sense. So I think I need to do something that's now closer to us on Earth, and that's also a big motivation for me to leave this behind me and to let other people unravel all the mysteries.
More questions or curiosities? Well, if not, sorry, apologies. One more question.
Thank you, Silke. Very nice presentation. If you go back to your final plot, the big one that shows how the curves change with the emulator versus from the default models. Yep.
Here, yes.
That one, yeah. So if I understand this correctly, this is for one time step, right?
No, so the radius you see here, radius can, in our case, or like in the case of circumstellar envelopes, just be translated to time because we have this constant velocity. So this is actually for, I don't know, it's like about, it's many seconds, millions of seconds that we evolve this. So it's not only one time step, it's really different time steps put after each other. And with every time step, also the density and the temperature is decreasing. So it's not one time step, it's really multiple time steps, like I think 130 time steps stuck after each other. And that was, I don't know if you have a further question, but it's nice to mention maybe to the audience that was one of the difficulties we encountered, because of course every time step in the real chemical model, it's all connected. If some molecule changes, that has an effect on the time step after that, and so we needed to incorporate that actually in our architecture. So in our training scheme, this was incorporated. I skipped that difficult part for this presentation, but it's actually a good point that you mentioned. It's really multiple time steps with changing physical parameters, and we're still able to predict it with this emulation.
Okay, so then my follow-up question is that whole time scale, that 130 time steps that you've used, how does that compare to the evolutionary phase of the AGB?
Okay, that's no. my answer sounds skeptical. No, the thing is, I'm not sure how long the AGB phase takes, but so in this case, what we do, it's indeed a bit strange. So we take a snapshot of the AGB star, and then that's just one piece in the evolutionary phase, and then we go out in the outflow. So the time steps I was talking about are chemical time steps and not really stellar time steps, if you know what I mean. So this radius, so it's this thing is really a snapshot of a certain point in the evolutionary phase of the AGB star, and then we're just starting from the AGB star and walking throughout the outflow and see what happens to the abundances. So I hope that answers your question.
It does. Thank you.
All right, more questions? Okay.
That's my mother.
So, Silke, we're really proud of you, of course, because it's a beautiful work. We have seen not the content, but more everything around for all these years.
Yeah.
And you know that we have kept on teasing you all the time, like, what the hell are you doing? This is so science fiction. What are we as humanity, just simple people? What does this contribute for us? And that's also a question, I think, for the jury and all your colleagues here, like, what is the world with what you are doing?
Okay.
The reason of her being, I know, but
okay, it's a fair question. It's also maybe a question I didn't want to be answering. No, okay, so it's true that maybe for daily life, these HB stars or general stars very far away from us that evolve on timescales much longer than our lives seem quite useless. But in this specific case, it's still about, in my case, it's about chemistry. And for example, with studying the chemistry in these stars, chemistry is universal, just like physics, but the environment in stars is much different from Earth. So actually, we can learn a lot about these chemical reaction rates that have come to mention during this talk. So in my specific case, we can learn something about chemistry. So all the things we model can maybe go back to the lab, and then we can ask people in the lab to really test more or do more experiments on certain molecules that we see behave strangely in the universe. But in like a bigger picture, I think in general, it's still important to study these stars, and because we just get to know a lot of knowledge about also physics and just fundamental science is maybe something that it's not immediately useful, but I think that history has proven by studying objects far away, we can also improve. Like, for example, I'm using machine learning. use certain techniques that might be in the end useful even for on Earth for this chemistry emulation. There's also chemistry happening in the atmosphere that can maybe done. Yeah, we can maybe solve that via similar methods that we are producing, and also in other fields within astronomy, we can hopefully use techniques we use there or we develop in astronomy that can be also be used to daily life. So there's a lot of potential in a lot of different fields, I think.
All right. More questions? No, if not, then the examination committee will withdraw to discuss. And I would like to invite Professor Yates to join us on the other link. So we'll meet you there in a few minutes.
Thank you. Oei, geen idee. Nee. Ja, het gaat allebei. Het gaat allebei. I shall also say you can sit down. You can sit down.
We stand here. Dames en heren, geachte collega's. Ik geef u kennis van de uitslag van de beraadslaging van de examencommissie aangesteld voor het proef van doctor in de wetenschappen fysica. Silke Maes heeft aan de faculteit een proefschrift voorgelegd handelend over modeling environments of evolved stars, morphology, chemical sensitivity en neural surrogate models, tot het verkrijgen van de graad van doctor in de wetenschappen fysica. En Silke Maes heeft dit proefschrift in een openbare zitting voor de examencommissie verdedigd. De examencommissie heeft vastgesteld dat zowel aan de wettelijke en de decretale bepalingen als aan de voorschriften van de universiteitsreglement ter zake wordt voldaan. Na beraadslaging verklaart de examencommissie dat Silke Maes voldaan heeft aan alle eisen voor de proef en de graad van doctor in de wetenschappen fysica behaald. Bijgevolgd en in de naam van de rector van de KU Leuven wordt Silke Maes gepromoveerd tot doctor in de wetenschappen fysica. Door het verkrijgen van het doctoraatdiploma verbindt u zich toe dat als dokter ook in de toekomst zal handelen in overeenstemming met de basisprincipes van wetenschappelijke integriteit, zoals beschreven in de ALEA Europese gedragcode, betrouwbaarheid, eerlijkheid, respect en verantwoordelijkheid. De zitting is gesloten.
Dank u wel. Ja, ik ga... Ja, oké, dank u. Ah, deze.
Een autograaf.
Ja, dat is goed. Ja, en hier mijn handtekening. Ah, dank u wel. Alsjeblieft.
En nu zullen de promotoren over u graag willen.
Ja.
All right. Silke, I wrote everything down, but before I wrote everything before I heard the questions of the audience. So perhaps there are some things that I probably should have changed, but we will discuss that later. So, Silke, we first met. So I first met Silke, or now I should say Dr. Maes, in her first year here in Leuven. Back then, I was a teaching assistant for her first course on electromagnetism. And I remember very well Silke and her friends all sitting in the same order, every week in the same order, on the second row in that classroom. And I think I even recognize some of the people who were back then. Yes, oh, yeah. Oh, they're still sitting in the same order. Not on the second row anymore. Oh, geez, this is quite intimate. Okay. Yes, and so I remember them, which is already something, especially because they were always asking questions. Many, but great questions. They really wanted to understand every detail of the physics. So I always had to make sure that I was super well prepared for these weekly interrogations. So I was very happy that I could now do the same thing on the website. Yeah, so although it were really interrogations, I really loved it. And I learned a lot from that experience. But you have to realize, you and your friends, you guys were pretty intimidating back then. So when a few years later, Silke joined our team for her master thesis, I must say I was a bit nervous because, yeah, there she was again.
It was my friends that asked the questions.
So yeah, there she was again. So I was nervous, but also thrilled because I already knew about your determination, about your scientific mindset, and it was clear that great things would come out of that. Yeah, so then for your PhD, it was first Marie who took Silke under her wings, but I'll let Marie talk about that later. And then only in the later years, we finally started working on Maes. After many discussions, after many talk about Maes or this emulator, this big thing that we were going to do. And Maes involved a lot of coding, a lot of trial, a lot of error. But luckily in the end, were more trials than errors, as you all could witness earlier today. But I want to give the audience a little bit of an idea of how this kind of collaboration, how this went. So Silke would come by to my office saying she had this or that problem, and then she would walk me through all the different things that she tried and all the things that didn't work. And usually, while she was explaining to me everything that she had tried, she actually solved the problem while explaining it, which left me there just saying, okay, yeah, great, just go do that. And so that was the inspiration for a gift that we have for you now. So in the future, if you ever need some supervision, we have this rubber ducky for you. And you can explain all your problems or all your ideas
Duck.
to the duck. And then if you want an answer, you can just read the card and it says, just do it. And it will probably be right.
Thank you.
Then another thing we learned about Silke is her, and that we actually also saw today, is her eye for detail. And I think it's safe to say that Silke is a little bit of a perfectionist, which is great. We've spent many hours commenting on slides and figures, adding, well, just a bit more space to the left or moving things just a bit more to the right. Great fun. Not so much for the person who had to make all the adjustments, but well, I really liked it. I especially liked the end results. But this also caused me some stress over the last week, because we wanted to gift you a set of stickers of your beautiful Maes logo.
Oh, wow.
But we didn't dare to order a whole batch without your approval, because yeah, I'm sure we need to move some things to the left and move some things to the right and adjust some colors. So tomorrow, some test samples will be delivered,
Okay.
and we can make all these necessary adjustments, and then you can order, well, we can order a whole batch and you have them for the conference next week.
That's cool.
As a preview, because you didn't show it in your slides, but
No, it's true. Now,
this is the logo that she designed.
I hope you see the design a little bit from the architecture thing.
Yes, there's a
But
whole
the colors
story.
can change. Yeah, thank you.
But probably the end result would look nothing like this, because it will be changed and everything will be completely different in the end. All right, finally, almost there. Silke, you mentioned in the beginning of your thesis, and also it comes a bit true in the questions from your parents, during your time, you asked sometimes, what am I doing? And sometimes you were worrying about having impact, about doing the right thing. And if there's one thing that you convinced me of over the last years, it is that whatever you do, you will have impact. Never worry about that. Every project you work on, every meeting you are in, you contribute and you make a difference. Sometimes it's just a very small difference of 2 pixels moving something to the left or to the right. But sometimes the difference is as big as the difference of being not able to do hydrochemistry, and now we are able to do hydrochemistry, which to some people might not seem like a lot of things, but it is a giant leap. Something that a whole bunch of scientists up until a few years ago were not able to do is now possible thanks to Silke. So yeah, I think that should speak for itself. So don't worry, just do your thing. You're great at it. Thank you for all your hard work and have a great future.
Thank you.
And there's some more stuff in the back, sorry.
I'll also look at it later like Jolien, or?
Yes.
That's fine, thank you. It makes some noise.
All right, Silke, part 2 of your speech, because you have 2 supervisors, co-supervisors. So the first time that I met you wasn't quite as scary as when Frederik met you. It wasn't part of an intimidating row of students, but I think the first time we met was when you were a master student of Wart. And Wart and I shared an office.
Yeah.
So I mostly associated you and Jolien as the 2 students that made Wart very enthusiastic and talk and talk and talk and talk. So whenever I saw you 2, I had to put my headphones on. But yeah, so that was my first impression. Still a great impression because you made Wart so enthusiastic in your master thesis. Both of your master theses were some great work. But the first time we met, when, well, maybe your proper first encounter was when I proofread your FWO application to see if there's anything that I could contribute chemistry-wise. And yes, there was. I was like, oh, this is great. We should do this. It would be amazing. Let's collaborate. Let's start working together. And so we did. And now you've become the first PhD student that I co-supervised, which was a great experience. And I learned a lot from supervising you and also the things that we just discussed. And I also want to thank you for that because you really pushed into, like, for my promotion to become a co-promoter. So thank you. And so it's been quite a journey because doing a PhD, as you already mentioned, it's not easy. And you started during COVID still.
Yes.
So travel was restricted. We weren't able to go to the office, but I read through your acknowledgements. We have to acknowledge Zoom. And I like to think that maybe our COVID times also prepared us for our sort of remote co-supervision dynamic that we had with our weekly Zoom meetings. So it did bring us some things in a way. So it has been wonderful to see you grow. And Frederik already mentioned that you're quite a natural leader and you make a real difference. And over the past 4 years, I've seen that you also, because you're a confident person, but your confidence in your science and your scientific abilities also grew a lot. You went from maybe being a bit hesitant starting a problem to now you just confidently navigate a big issue. You tackle the issue, you break it up into small parts, and you just do it. You've really become the captain of your own research. So, oh wait, I'm losing my thread. Good thing that I made some notes. So a particular moment of being a proud supervisor was quite similar to like what Frederik described, but that came a bit later. So it was a few years before when we were discussing the chemistry. And you asked, well, like, but why is this molecule behaving this way? Like, I don't get it, but maybe, oh, yeah. And then you just talk through the entire network and all the pathways that were possible. And you just answered your own question and be like, oh, she knows. Oh, it's amazing. Oh, look at her. It's wonderful. That was a great and a proud supervisor moment. So you really took the chemistry and you ran with it. And you ran with it all the way to Leeds, where you visited me for a week and where we collaborated in person for a while. That was a change for us. And you also, at chemistry, took you all the way to the US, to Traverse City, just a small village near a lake. Oh, all right, okay, we went there. And there I have to thank you again for buying some painkillers for my foot. So thank you, Silke. You made me walk a bit longer. It also took you all the way to Melbourne just 2 months ago, where we socialized a lot. And also it was very nice to shepherd you and Jolien to and from the university from South Yarra. And the next week, I expect that we'll have some nice times in Leiden and you can hand out your prototype stickers. So I hope that you learned a lot. Well, you clearly learned a lot during your PhD, but I also want to mention some things that I learned from you, because you have a very nice approach to work and like outside of work that I want to implement. So I'm not going to accumulate all my holidays and then just take a month off at the end of the year. No, I'm going to go on small adventures just like you do. And I would also sort of maybe get a bit of your feeling with dealing with people and leading people and how to engage you engage with people around you and bring them together. So it's been clear from your presentation, from your thesis, that Maes really is the pièce de résistance of your PhD and all the things that you learned about computer science, machine learning. I think they guarantee you a very bright future. No matter what you do, you will always find a wonderful job that will motivate you and interest you. But you shouldn't forget where you came from, about the chemistry of it all. And as a reminder of this chemistry, there's something that I would like to give you. So now I'm going to do like a very
Molecules?
sneaky. There's a few molecules. Yeah, there's some in the air for you, especially okay, some rustling. Okay, so this is I'll try to open the box. Here you go. This is a piece of a meteorite.
Oh, wow.
So as you move away from science, you still have some bits of AGB chemistry to carry with you, because I'm sure they're encapsulated in this carbonaceous polymerite. So thank you for the wonderful 4 years, and well, I don't need to wish you good luck. I think, well, no, I will still wish you good luck because that's just like, oh, knock on wood now. But you have a very bright future ahead of you. So thank you.
Thank you. Okay, so I guess now it's my time. First of all, both of you, thank you so much for the nice speeches. I was also thinking maybe you should hop along with job interviews with me because you can sell me very well. But no, I agree. It was a great collaboration with both of you. I think I wrote in I haven't prepared, so I'm just babbling. No, the two of you are really my academic big brother and academic big sister, as I wrote down, and it really felt like that. It didn't feel like talking to some supervisors that's much higher, but it felt like a chat with like, yeah, sort of academic siblings. And yeah, so I won't say too much, just a very big thank you and all the nice words. And also thank you, of course, to Lynn. You're also very supportive, and you gave me the freedom to also not explore only the research, but also explore like the outreach projects that I did. And I was also a representative at the department. And thanks to you, you gave me the time and the space for this. And that's also helped in like developing all of these skills that you were talking about. It's not only due to this research and the PhD, but it's due to all these things. And I also have a gift for you, of course. I know the three of you are more coffee drinkers, but as you probably, I don't know if you know, but people around the IVS know that I'm quite of a tea fan. So I wanted to give the three of you something that I value. And so I picked out a special tea for each of you. So this is, and there's also a card that you can read later. There. And then this one's for Frederik and the cards, and then also one for Leon. So I picked out a special tea. So I hope you will enjoy it from time to time and then think back to all the collaborations. And so, yeah, so I think that's all to you. And then thank you everyone here. Of course, my family for supporting, all my friends and colleagues for supporting me. So, and thank you especially for joining today. I hope you learned a bit about the HB stars, but also just had a good time. And then now it's time for the real celebration. So, so there is a so there is a reception. It's again around the building. Like I've pointed many people to the toilet, so it's close there. It's even one stairs up. There's quite some different drinks, so don't only drink the cava. There's other stuff, also alcohol-free options. I just want to mention them. I also just the last part. I want to leave a copy of my thesis where you can all maybe leave a note if you feel up for it. So I hope to put that somewhere, but then I've already mentioned it to you that you can find it. So thank you all, and please go enjoy the reception.
Mag jij het kaartje toch? Had jij het kaartje? Hier. Ja, dat zit in is het nog een kaartje? Oh. Dank u, ja. Goed gedaan.